In note sheet number 6, we're going to add a couple more patterns to our proofwriting repertoire, and also in the context of a diagram where the triangles happen to be overlapping. And so the new patterns that we're using today have to do with isosceles triangles, and in the first pattern, the sides to angles pattern, if you have a triangle and you know that two sides are congruent, then, as you recall from a previous unit, the angles that are opposite those sides will be congruent as well. So if segments AB and BC are congruent, we can conclude that angle C and angle A are congruent. And the reason that we'll use, I'll refer to this as if sides then angles, which is if two sides of a triangle are congruent, then the angles opposite them are congruent. The converse of that is also true in the angles to sides pattern. So let's say we knew that angle W and angle Y were congruent, then the sides opposite those angles will also be congruent. So segment WX and segment XY would be congruent, and then our reason is just the converse of the reason that we used up above. If two angles are congruent in a triangle, then the sides opposite those angles are congruent as well. And so when you have a diagram such as this, where your triangles are overlapping, it may be helpful to pull them apart before you start labeling in order to help you complete the proof. So before we start marking up the diagram, I'm going to go ahead and redraw the triangles. And so we've got the triangle on the left, triangle PSN, and then the triangle on the right, triangle TRV. And so I'm going to label all of the given information, and I'll label it in both the original diagram as well as the pulled apart diagram, just to help us to see the angles and sides that are going to be congruent. So our first given is that segment PR is congruent to segment ST, and notice that that given doesn't give us a pair of entire sides that are going to be congruent, but we'll be able to use segment RS to help us. Another given that we know is that angle N is congruent to angle V, and so we can label that in the redrawn diagram as well. And then we also have that angle P is congruent to angle T, which is these two angles up in the redrawn diagram. So in the redrawn diagram, right now we have two pairs of angles. We're going to need a pair of sides. And if we go back to what this first given was telling us, we know that segments PR and ST are congruent. Segment RS, if we were to add that segment onto both PR and ST, then what we'll be able to get is that segment PS and segment RT will be congruent as well, and that's going to help us to get our two triangles congruent, and that's going to be by AAS. So now that we've got everything marked, pause the video and then see if you can fill in all of the boxes to complete the proof. So in the proof, two things that we can fill in right away are two of our givens. The two pairs of angles that we were given are congruent. Those were angles that were in the triangles. So that can go directly into the 3-to-1 connector. And then in order to get our pair of sides, there was a little bit more work that we needed to do. So the first given that told us that segments PR and ST were congruent, if we added on segment RS to each of those segments, we would get that segment PS is congruent to segment RT, and that's by addition. And then, as we had already said, the two triangles, triangle PSN and triangle TRV, will be congruent by AAS. Now we also need to figure out how to get that triangle WRS is going to be isosceles. And remember that an isosceles triangle is one in which you have at least two sides that are congruent. So because the definition mentions sides being congruent, that's going to be what's in the box immediately preceding our final statement. So we're going to be able to get these two sides congruent. That's what we'll need in order to say that triangle WRS is isosceles, but those two segments we can't say are congruent by CPCTC because they're not entire sides of the triangles that we just proved congruent. However, what we can do is use CPCTC to get those two angles congruent. And then once we have that those two angles are congruent, then we can say those sides opposite the angles are congruent. And now that we have those two segments congruent, we can say that triangle WRS is isosceles. And the reason for that would be the definition of isosceles triangle. And that completes our proof. What might be the most challenging about this next proof is determining which pair of triangles we need to get congruent. And it's usually helpful to look at what statement you're trying to prove, and in this case we're trying to get that angle ECB is congruent to angle DBC. So we may want to look for a pair of triangles that actually have those as angles, and so angle ECB is in triangle ECB, and then angle DBC is in triangle DBC. So let's maybe start by trying to get those two triangles congruent, and then if we can, then it would be just a quick CPCTC statement that will allow us to get angles ECB and DBC. So I've gone ahead and pulled apart those triangles so that we could label both the original diagram and the redrawn diagram. And let's see what we know. So we have that segments AE and AD are congruent, and those don't appear in our redrawn diagram. We do know that segments DC and EB are congruent. We can also mark that in our pulled apart triangles. Notice that we also have segment CB happens to be shared by the two triangles. So we've already got two pairs of sides. We would be able to get those triangles congruent if we either had the third pair of sides, and we could do an SSS proof, or if we had a pair of included angles, and we can do an SAS proof. Take a moment, pause the video, and see if you can figure out if we can get one of those two pairs of things. So what you may have noticed is we would be able to get segments AC and AB congruent by addition, since we know segments AD and AE are congruent, as well as segments DC and EB are congruent. So if we know segments AC and AB are congruent, that means we have an isosceles triangle. Therefore, if those two sides are congruent, then the angles opposite those sides are going to be congruent as well. And so that is angle DCB and angle EBC in our pulled apart triangles. So we're going to be able to get these two triangles, triangle DCB and triangle EBC. We're going to get those congruent by SAS. So again, go ahead and pause the video. Now that we've got a plan for getting our triangles congruent, go ahead and see how many of the boxes you can fill in on your own. So I began by filling in a couple of pieces of information that immediately get us pairs of things in the triangles. One of our givens was that segment DC was congruent to segment EB, so that can go immediately into our 3-to-1 connector. And then we also had, for the two triangles that we were trying to get congruent, there was a side that was shared by both of them. So segment CB is congruent to segment CB by reflexive. And then in order to get our pair of angles congruent, that required a little bit more work. We can take both of our givens, and you'll note on your sheet there that it says you may use a given more than once. So both of those givens together allowed us to get that segments AC and AB were congruent by addition. And so then we're able to get those two angles, angle DCB and angle EBC congruent by if sides, then angles. Keep in mind that you can name those angles a couple of different ways. I chose to use a three-letter name here as opposed to numbers because it might be a little bit tricky how to put those numbers in the diagram, but there's different ways that you could name the angles using three letters as well. And so, as we already mentioned, the two triangles, triangle EBC, triangle ECB and triangle DBC are congruent by SAS, which means then we can get the angles that we need by CPCTC. And then that completes our proof. Just be careful of your notation. In our final box, it's angles that we're talking about. In the previous box, it was triangles that we're talking about.